Hi, everyone. I guess you can hear me. Yeah, so my talk is going to be, I'm going to talk about software testing. And essentially, I want to kind of two talks in it for the price of one here. I would like to, so there have been quite a bit of progress on automating software testing and test generation using program analysis over the last 10, 15 years, 21st century. And so that's going to be the main part of my talk. And then I'm going to also talk about some current trends in the software industry and their impact on software testing. That's the second and shorter part. So, the main technical problem that I'm going to talk about here is automatic code-driven test generation. So imagine we have a sequential program and with a set of input parameters, a known set of inputs, interface. And then the goal is to generate automatically a set of inputs that when you execute the program with these inputs, you maximize code coverage. So exactly what code coverage? Well, let's say it's instruction coverage. It doesn't really matter for the purpose of this talk. So here, the goal is to automate test generation using program analysis. So for instance, if I have like this program, PowerPoint, which I'm using here, the goal, for instance, for PowerPoint is to generate automatically a set of PowerPoint file presentations such that if I execute PowerPoint with this set of files, I would maximize code coverage of PowerPoint itself, the program. So for instance, I could get like 50%, 70% code coverage, for instance. That would be great. Now, PowerPoint is a very complicated program. So I'm not talking about like a program that fit on one page or something like that. Millions of lines of code, complex input format, dynamic memory allocation, I mean, real programs, right? So this automatic code-driven test generation problem has been discussed for decades in the research literature. So for instance, you can find papers about this topic even starting 40 years ago. And so there are essentially two main techniques, two main approaches to address this problem. The first one is so-called static test generation. So in static test generation, you access the code of the program and do a static analysis that you can read it. You cannot run it. You can just read it. A tool can read the program. And the goal is to partition the program's input space into equivalence classes, such as two inputs are equivalent if when you run the program on them, they will exercise the same control flow path of the program. Unfortunately, static test generation is ineffective in practice for large and complex programs because symbolic reasoning is imprecise. And that's why there's so many papers in program analysis cycles about the trade-offs between cost and precision. And it's due to many different reasons. I mean, you can have pointer manipulation, complex arithmetic, system calls, etc. So just to illustrate the problem here, especially the limitation of static test generation, let's consider this little program here, which takes two inputs, x and y, integers, as input. And then the program tests if x equals hash of y, and then there's an error. Otherwise, there's no error. And assume hash is a very complex function. Perhaps it's a hash function or a crypto function. Or it's a code. We don't have access to the code of hash. Or maybe it's a million line of code. It's very complicated, and we cannot represent, we do not know exactly its behavior. So now, in test generation, the goal is to provide a value, a pair of value for x and y, such that it is guaranteed that it goes there or there. And in a program like this, since we do not know anything about hash, static test generation is not possible. So, another approach to test generation is so-called dynamic test generation. And in dynamic test generation, one is allowed to run the program. So for instance, we can run the program, perhaps starting with some random inputs, and then observe what it does, and gather constraints on test on these inputs, and then solve these constraints and generate new tests. I'm going to illustrate this with an example in a minute. And then we can repeat this process until, for instance, a specific statement, like an assertion, for instance, of interest is being reached. And there are papers in the 90s discussing these schemes. Or it also can be possible to combine this dynamic test generation with like so-called model checking techniques or systematic state space exploration techniques, where there the goal of the combination is to cover as many program statements as possible, but in non-property guided manner. And so in each execution, one checks lots of properties by using runtime checkers like purify, valgrind, app verifier. So I'm going to go more slowly in this in a minute. So why dynamic test generation? So let's consider to the same program here as before, okay? So now in dynamic test generation, we are allowed to run can run the code. So for instance, we can pick random value for x and y, like this x equals 33 and y equals 42. Sorry, x equals 33 and y equals 42. And then we run the program as usual, concretely, with concrete value, but also symbolically and dynamically. So this means that at each step of the execution, we symbolically execute the program. Symbolic execution means that we can run the program with symbolic values. We have one symbolic value associated with each input. And whenever there's a test involving an input, we emit a constraint like this. So here we observe that hash of 42 is actually 567. And then 33 is different from 567, so we're going to take the else branch of this test. And we can emit this constraint. But to make the comparison fair, we still don't know what hash does, or it's too complicated, so we cannot emit a constraint that would be solved by a constraint solver. However, now we have access to runtime value, and we know that hash of 42 is 557, so we can simplify these two complex constraints by a simplified one, by replacing hash of y by its concrete value, for instance, here. X different, and this constraint is, of course, easy to solve. And now we need a new pair of inputs, y42, x67, and then we hit the error. So in this case, so static test generation is completely helpless, and dynamic test generation, we generate two tests. We have 100% code coverage, we find the error, and we have 0 false alarms. So the point is that dynamic test generation extends static test generation, is more powerful, it's more precise, because it can leverage runtime information. And so this is actually, to my knowledge, the most precise form of test generation known today, and that's why it's been interesting development, and there are lots of tools that use this, and I'm going to talk about this in the next slide. So now you will say, well, this is still pretty naive because the number of program paths can be infinite. For instance, if you have a program and you have a single loop, which the number of iterations depends on some unbounded input, you may have infinitely many program paths. And yes, that's true, but in practice, you can use tricks, heuristics, for instance, to guide the search, and you can also prune the search space, and then still these techniques works well on small programs and in implementation. And compared to random testing, it's better because you can drive, for instance, the program along more code path more quickly. So how do you do symbolic execution? What constraint do you generate? And how do you solve them? Well, it depends. It's like in static program analysis, it depends. So it depends on the program, it depends on the interface of the program and with its environment, and it depends on the type of property that you want to solve. And over the last 10 years or so, there have been an explosion with dozens of tools implement these techniques and have extended them and applied for various purposes. So there's been a lot of work in that space. Another also interesting development is the rise of so-called SMT solvers, which also coincided like almost the last 10 years or so. So if you don't know what an SMT solver is, so probably you know what a SAT solver is. So if you have a formula of propositional logic, a SAT solver is going to tell you whether a formula of propositional logic is satisfiable or not, and if it's satisfiable, it will give you a satisfying assignment. Like this formula here of propositional logic is satisfiable if you set P equal true and Q equal false. So this is this is an NP-complete problem. And so with SMT solvers, SMT stands for satisfiability modular theories. When you have like a problem domain like software, you can generate formulas that are more expressive. So like for instance here, this formula involves arithmetic, array theories, which model memory accesses like read and write, and also uninterpreted functions, which are basically used to reason about program parts that you don't want to reason precisely about. And then if you feed a formula like this to an SMT solver, if you're lucky, you will terminate and tell you whether or not the formula is satisfiable. And if it's satisfiable, it will give you also a satisfying assignment. And there's been a lot of progress over the last 10 years in the engineering and the algorithm that are used in this class of solvers. And so today, actually, this dynamic test generation is the #1 application for SMT solvers as measured by CPU usage. And there is one project in particular, which is the main project that I've been working on since joining Microsoft in 2006, which is called SAGE. And this is a tool for security testing. So why do we use so much SMT solvers? Let me tell you another story here. So the context, the motivation of this work is security testing. So every second Tuesday of every month, so it's Patch Tuesday, Microsoft releases a bunch of security bulletins, which are patches that correct mistakes and are related to security. And these patches have to be deployed to nearly 1 billion machines everywhere on the planet. So, so every month we have like 5, 10, sometimes a little bit more security bulletin, and you can think of the direct cost of each of these bulletins to Microsoft being $1 million or more. So historically, many of these patches fix security vulnerabilities in programs that are processing data that are embedded in files or packets that are that are transmitted over the internet. So for instance, Windows client running on this machine supports hundreds of file formats and hence has hundreds of parsers, programs that read these inputs, like for fonts and video, images, sound, and so on. So from a research point of view, this is an interesting problem because it's like hunting for $1 million bugs, right? So what kind of bugs am I talking about here? It's mostly good old-fashioned buffer overflows, memory corruption errors. That's what I'm going to talk about here in this work, and that's what SAGE is aimed at. So, so I'm not a security expert, but to my knowledge, there are two main techniques used by black hats today to find security vulnerabilities in software, our software at Microsoft and other people's software. One is code inspection, often of binaries, and also the other one is so-called black box fuzzing. So black box fuzzing, or black box fuzz testing, it's very simple conceptually. It's a form of random testing. So if you have an application like PowerPoint, for instance, you start with a well-formed PowerPoint presentation, and then you randomly fuzz it. So you mixed a few bytes here and there, and then you run PowerPoint, and then you see if you can trigger a buffer overflow, a memory corruption error. And so that's as simple as that. That's black box fuzzing. Sometimes black box fuzzing enhanced using grammar-based representation of the input format. So for instance, if you know that PowerPoint format respects some rules, you can have a grammar, or partial grammar, that encode these rules. And then there you can also encode heuristics to fuzz. So for instance, you could say, oh, these 4 bytes are interpreted as an int, for instance, a signed int. And then try more often 0 when you fuzz, 0 or -1 or some specific value. So you have production rule over grammars associated with probabilistic weight, and you can control this way how the fuzzing is being done. So conceptually very simple, but has been shown to be very effective in finding bugs. And so, so fuzzing is heavily used in security testing. So for instance, you can buy this book for like about $30 US. It's called the SDL, the Security Development Lifecycle. And so this describes how we develop software at Microsoft from a security point of view, and we recommend other people to use similar kind of techniques. And so, for instance, at Microsoft, fuzzing is mandatory for every unentrusted interfaces of every product. So every product, in principle, has to have a review at the architectural level, where, from a security point of view, all the untrusted interface of the product are being identified. So where you can take in untrusted data. And then fuzzing is mandatory at those interfaces. Yeah. So when we started this project, this was basically the state of the art. And starting like around 2006 or so, we started developing a new approach to fuzzing, which we call white box fuzzing. And the idea is to use these dynamic test generation techniques and to mix them with heuristics used in the fuzzing community, and to apply them to security testing of large application. So why do we use dynamic test generation and dynamic symbolic execution? Because this is the most precise form of test generation that I know of, and most precision is that's why SAGE, for instance, this tool that implements these techniques, is going to be able to find more bugs than less precise techniques, like black box fuzzing. So compared to prior work at the time, so here the emphasis on large application like PowerPoint. It's not for unit testing. We're going to steal some tricks from the fuzzing community, like for instance, starting from well-formed inputs, which is going to give us much better coverage from the beginning of the search, and use techniques that are going to be leveraging symbolic execution that are very expensive. So I'm going to come back to this in a minute. And so this was implemented in this tool, Sage, that I'm talking about here. So let me illustrate what's going on here with a simple example. So imagine I have this program here that takes 4 bytes as input, and then it has a local variable, a counter, which is initially 0. And if the first byte is B, the counter is incremented. The second byte is A, and then so on. The counter is incremented, and the counter is 4, then there is a crash. So the goal is to try to find the crash, for instance, okay? So we start with an input here. I mean, here it's just a string, but let's say a well-formed input. I mean, here it's an artificial example, but let's say good. And then we run the program, both concretely and symbolically. So concretely, here, the first input is G, it's not B. So we're going to take the else branch of this branch. And then we're going to detect it, and then when we hit this, we run this, in dynamic symbolic execution, we'll emit this constraint that the first byte is different from B. And then dynamically, you observe that the second byte is different from A, and so on. And so this is a conjunction of constraints, which is called a path constraint, which basically, it defines also an equivalence class of program inputs that drive the program to the same control flow path. And so now we're going to generate each constraint one by one here. So we take the last one, for instance. We start with the last one, and we negate it. So instead of being the last byte being different from exclamation mark, now it's forced it to be exclamation mark. And then we take this constraint and the conjunction of constraint, and we add a new pass constraint. We feed that to an SMT solver, and we give the solver like 5 seconds max. And if it can find a satisfying assignment, it gives it, if it says it's satisfiable, then we get a new input, which is a fuzzed modification of the previous one that will drive the program, that should drive the program along the same path, except for the last branch here, which we take the other branch for the last test. And so in this way, we repeat the process, and for one symbolic execution, we get 4 new inputs this way. And we repeat the process. So these techniques are inspired. So in a toy example like this, the search space is small, and the search space can be exhausted. And if symbolic execution has no imprecision, we actually have verification, as in formal verification. So a tool like Sage for toy example like this actually perform exhaustive testing, also known as software model checking, and it can be a verification. But in practice, we are not going to be having verification because the search space are going to be huge. So to give you an idea, if you run Excel on a 45,000 input bytes spreadsheet, for instance, a sample one, you will symbolically execute nearly 1 billion x86 instructions. It may take half an hour on a modern machine. After throwing away a lot of constraints, you might have, due to heuristics that I don't have time to talk about here, you might have 6,500 constraints that you call each one of them. There's one call to the SMT solver for each of them. And then you might get 3,000 of them are satisfiable, and you get 3,000 new tests. So, Sage, this white box fuzzing approach was introduced in this Sage tool. And one or another key feature of the tool is that it works with x86 execution traces, which is kind of scary in a way. We don't need source code to use these techniques. It's optimized for so-called file fuzzing, so it focuses on file processing application, like PowerPoint, for instance, where the untrusted, as a user, you specify which file is untrusted, and then every byte read of that file will be marked as symbolic. And that's basically the input space that we're trying to find input value for in order to find bugs. And it's optimized to handle use execution traces, symbolic execution of billions of x86 instructions. So looking under the hood, this is how Sage works, roughly speaking. So let's say we have an application like PowerPoint. We start with one well-formed input. In practice, we use usually, as in fuzzing, a set of inputs. But so one for each input, we run the program, and we use this like a runtime oracle, like app verifier, a runtime checker, like app verifier, so it's like purifier, valgrind, etc., which is going to basically map memory corruption to crashes so we can detect them. So if there's no crash, then we're also going to collect card coverage information. So here it's instruction coverage. So we compute all the unique instruction being covered during that execution, and we store it. And then comes the expansive part. We do dynamic symbolic execution. And so in the case of Sage, actually, we replay the program, but it's a detail. And so here, this basically is, this could be like symbolic execution. There it might be 1,000x basically, slower, to give you an idea. And so we're in a single symbolic execution, and we may perhaps generate 1,000 constraints, let's say. And now we invoke the constraint solver, the SMT solver, for each of these constraints. So let's say we have 1,000 constraints and 500 are satisfiable. We get 500 new tests. And now we repeat the loop. For each of these tests, we see if we have a bug. And if not, we compute incremental coverage. Let's say the first input discovers 100 new instructions. Now it gets a score of 100. The second one discovers 0 new instruction. It gets a score of 0, and so on. And then we pick the winner, let's say 100. And it goes back to symbolic execution, generate new tests, and so on. So you get the idea. So this, we run this for weeks at a time, month at a time, basically. So that's why it takes so much computational effort here. So we started using this tool really in 2007. And it turns out it's a very effective way of finding security vulnerabilities in file parsers, especially for binary formats. And so we basically, what kind of application am I talking about? So image decoders, media players, document processors, etc. So internally, Windows and Office are our biggest customers inside Microsoft. So what kind of bugs? So buffer overflow type of bugs. And so many security critical. And so to give you an idea, so when we started deploying this in 2007 and then on a large scale in 2008, 2009, and so Windows 7 was shipped somewhere in 2009, I believe it was 2009, yep. And Sage was credited to have found about 1/3 of all the file fuzzing bugs found during the development of Windows 7. And because Sage was new at the time, it was run really last. And so we know that all the bugs found by Sage were missed by everything else. And what is everything else? Well, it's regression testing and black box fuzzing, grammar-based fuzzing sometimes when it's applied. So grammar-based fuzzing is labor-intensive. Grammar-based fuzzing is as good as your grammar, and your grammar is as good as the person who writes the grammar, and it's human time, etc. So it's expensive. While black box fuzzing and Sage are purely automatic. There's no human intervention necessary for our application. And also missed by static analysis, which is used much earlier in the development process. So, some information about the impact of Sage. So we've been running Sage for over 500 machine years. And so to my knowledge, it's the largest computational usage ever for an SMT solver. We found quite a few bugs and saved quite a few security bulletins. And so if you use PowerPoint, if you use Word, if you use Excel, if you look at an image on a Windows PC or a video, well, you have been impacted by this work. Probably you didn't know about it, and that's the way we want it to be, but you've been very directly impacted by this type of work. Another quote, another data point that I really like is this one about like practical verification. So to my knowledge, since 2011, there have been 0 Patch Tuesday bug security bulletin issued on all the Sage-cleaned binary Windows parsers. So this means that, so if nobody in this room, nobody on the planet can find the bugs anymore in these applications, it's as if they are correct, right? That's all we need in practice, right? So what the practical value of this work is to reduce the cost and risk for Microsoft and increase the cost for hackers to find bugs in these applications. And if you raise the bar sufficiently high, well, they can't find anything anymore. And from a security point of view, that may be good enough. So what's next? What are the big research challenges in this area of research? Well, there are at least 2. One is to, of course, to try to come up with this, the dream of formal verification for these large applications. For something like PowerPoint, for instance, we still don't have tools today, automatic tools, that would prove that there are no more buffer overflows. By prove, I mean mathematically proof. So this is an active area of research. Another thing is that, well, to have more applications. So I was bragging about this 500 machine years, basically. which is, I think, the world record for the moment in this space, but yet 500 machine years is nothing compared to the CPU usage for other problems in computer science, right? So it would be great to have other application for this type of techniques where they are effective and economically feasible to use this type of techniques. And this is, of course, an active area of research as well. So there is much more about this work that I won't be able to talk about here. How do you deal with loops, pointers, and floating point instruction? What property do we check? And how do you scale symbolic execution for billion of XLS instruction, etc. You can go to my webpage or talk to me offline if you want more about this. And this is also joint work with a lot of people over the years. So in the second part here, I thought I would talk a little bit about some current trends in the software industry and their impact on software testing and verification, and also illustrated with some example from Microsoft. So over the last 10 years or so, 10, 15 years, one thing that has a huge impact on the software development for client software is the availability of telemetry. So if you use Windows and you have a crash of an application on Windows, you may have seen a window like this popping up where you want to say, well, so the program has been crashing, do you want to send more information about the problem to Microsoft? And so maybe often you don't click, or you click cancel or something, you don't click yes, but when you have 1 billion users, you have quite a few people who send this information. And so every day we receive millions of reports like that. And then they are bucketized and triaged automatically. And this gives you basically tremendous feedback about what's going on in the field. And most of the time, I mean, you have like a few root causes that most experience, like 50% of the crashes can be bucketized in very few buckets. And so this way, this is a great tool to help prioritize where you should basically focus your effort in order to improve the quality, the perceived quality of a product. And so this Windows error reporting has had a lot of influence about improving the quality for client software application. And this is not just for Microsoft, actually. So if you have an application that runs on Windows, you can subscribe to a program where if your application crashes on a PC, you get the report. You can see the reports that go for your application. So another, of course, another new thing, so to speak, that arises really about the last 10, 15 years is A/B testing. So, and this is mostly for services software. So here, this is Google, this is Bing. If you're working on a search engine, well, there's a lot of testing that you don't have to do really upfront that much because you can use, so for some classes of features, your users as your testers, right? So you can basically, since everything on the service side, you can have a small amount of your users switching to the new version of the software and then see if everything goes doing monitoring and log analysis, and if everybody's happy and there are no major things, you gradually basically move everybody to the new version. So this changed dramatically from a testing point of view, the amount of testing and the type of testing that you do up front. So of course, there's a lot of, in the software industry these days, a lot of basically effort and activity around developing software for smartphones and cloud. So how much testing do you need for this type of application? Well, it varies very widely. I mean, there are many apps on smartphones that are poorly tested or not tested at all. But then there are some apps for which correctness is very important. I mean, correctness or reliability or security, and so it varies a lot. Diversity is really the key word here, I think. So the cloud is also an opportunity for advances in program analysis. So there is a trend in moving more and more of the software development assets, stuff, to the cloud itself. You have IDEs, integrated development environment, where the code itself resides in the cloud, and you edit it, and it's in the cloud, and it's built in the cloud, and it's tested in the cloud. And so you have all these artifacts that are there in the cloud in a centralized manner. So there are tools that are emerging that are doing basically kind of big data and cloud analysis for software engineering. So for instance, at Microsoft Research, we have tools that start to emerge and being used actually in production that mine data about the code a code complexity, and also edits code churn, right? And then bug database, the history of the code and how many bugs were, what kind of bugs were there, etc. HR data, so who's touching the code, in which organization? Is it a tester, a developer, how senior, junior is the person, and so on. And then can, for instance, generate pretty accurate fault prediction models where, for instance, if you touch the code, that line of code, then you have a 20% chance of actually introducing a bug. Well, if this other person touches the code, it has perhaps 30% chance for doing that specific code change of introducing a bug. So you have like this more and more sophisticated tools that are emerging and transitioning from research cycles to more and more mainstream software development. And then, of course, there is the rapidly expanding world of computing, where computing is everywhere. So Internet of Things kind of, Internet of Things stuff, basically, for instance, a big buzzword these days. And so there are many new challenges, like, for instance, machine learning. How do you test and debug machine learning application? How do you measure security? How do you test efficiently for privacy? So there are many, many new problems, and all problems that need to be revisited and that are becoming more and more economically relevant and crucial in this new world. So to conclude, in this talk, I wanted to give you a quick overview of some recent advances of automating software testing using advances in program analysis that have taken place over the last 10, 15 years, the 21st century thing in the title. And mention some application, and including also a new area of research. And then I wanted to mention briefly some current trends in the software industry and their impact on software testing. And so we live in a world of remarkable innovation, diversity, and opportunity, and the same is true for software testing and verification, both the research and the tools themselves and the application. That's all I have, so thank you very much for your attention.